All right, guys, let's go ahead and get started. Modifying our schedule this week. I think I had told you quiz Wednesday and then finish up lecture Thursday. That was based on kind of my two classes in my mind that I'm trying to hold together. We'll be done with lecture today. Look at what we have left, and we'll be wrapping up today. So we will use Thursday for our quiz, and then tomorrow we won't even need to meet. So no class tomorrow. I'll be here. If you need to see me for anything, if you need to review anything, I'll go over at the end of lecture today what to expect for that quiz. But quiz will be Thursday, and then again, like I said, we'll wrap up lecture today. So either before or after the quiz on Thursday, if there's anything that needs to be reviewed, we can do that on Thursday, and then the final will be next Tuesday. Questions before we get going on today's material?
Is that our last day of class then?
What's that?
Our last day of class then is on Tuesday?
Correct. And we don't meet Monday. Other questions? All right, the last thing last week that we talked about was real briefly was the function of the nephron loop. It'll come up again later in today's discussion, but we said that the function of the nephron loop was to create this high concentration of sodium chloride. So in other words, we created this salinity gradient, this salty environment within these renal pyramids. So within the renal pyramid, a salty environment is created by the nephron loop, and later we'll see how that affects our ability to conserve and adjust the water concentration of the urine that we produce. Today, and essentially, there's some vocab at the end of the unit, but this is the last kind of major conceptual item that we have left to cover in our urinary system unit. We're going to talk about the 4 major hormones that influence urine formation. We've talked about this back when we were talking about how we modify and control glomerular filtration rate. We said that there were multiple mechanisms. There was the renal autoregulation, and there were 2 different ways there, through the myogenic and the juxtaglomerular method. But once we got to hormones, we said hormones help regulate, and we'll talk about it in greater detail later. So here's where we'll kind of bring the hormones back into relationship with the GFR, but we'll also talk about just other things that these hormones affect in our ability to either conserve water, secrete particular waste, reabsorb particular electrolytes. Hormones, through the production of these hormones through the endocrine system, are going to influence urine production and urine formation in a few different ways. So listed here are simply the 4. We've got aldosterone, atrial natriuretic peptide, ADH, or antidiuretic hormone, that's ADH, and then parathyroid hormone. For each of these, you want to be thinking about 3 things. First, very simply, you want to think about where this is coming from. Right? Where, in what organ or tissue of the body is this particular hormone secreted from? Generally, what are the reasons for its secretion? So if we're going to release this hormone, what led to its release? What were the conditions under by which we decided we need to release this particular hormone? And then 3, what are the effects or the mechanisms of action, sometimes is how we refer to it, that these hormones will have on the urinary system? And then some other kind of extended functions on, or extended actions on other systems of the body as well. So again, just to kind of frame the way we ought to think about these hormones, where are they produced, where do they come from, when do we secrete them, what are the conditions under that we might secrete these hormones, and then 3, what do they do? What are the mechanisms of action as they relate to either the urinary system or maybe some other related system here that we'll discuss. We're just going to take them one at a time and stop me where you have questions, and we'll see if we can't get each one of those questions answered for any one of those. All right, so the first one, aldosterone. Right off the bat, underneath there, it tells us that it's secreted by the adrenal cortex, we can modify and simplify that to just simply the adrenal gland. The adrenal gland, we haven't mentioned it before, maybe you've noticed it on diagrams or maybe noticed it on the model of the kidney in lab, but it is just an endocrine gland that sits on top of the kidney. So the adrenal gland, specifically the cortex, but the adrenal gland would be our low-hanging fruit for this one. So where does aldosterone come from? It's produced by the adrenal gland. The nickname of aldosterone is the salt-retaining hormone, which ties into at least one of the reasons why we might secrete it. Maybe we're low on sodium, maybe we're low on chloride, or maybe we're low on both. So down below, it says triggers for aldosterone secretion. This is that, why might we secrete this particular hormone? So the reasons for why we typically might secrete aldosterone is maybe we have low sodium levels in the bloodstream. So aldosterone helps us reclaim sodium that would otherwise go to urinary waste. So when we secrete aldosterone, it's basically the endocrine system telling the kidney, hey, pull all the sodium that you can out of your urinary waste, because we're simply low on it right now. So if somebody has low sodium levels, we could probably assume safely that aldosterone is going to be released from their adrenal glands. The other reason, when potassium concentrations are too high. So we might also secrete this if we have too high of potassium levels. This would be probably less likely, but it's another condition under which we might secrete aldosterone. And then the last one is if there is a drop in blood pressure. So if we have low blood pressure, systemic throughout our body, if we have low blood pressure, aldosterone will help us increase the blood pressure through a mechanism that we'll describe in just a second. Okay, so we tackled hopefully at least the first two there, right? Where does it come from, and when do we secrete it? Questions there? Yes?
So if someone has consistently like low blood pressure, what would be considered low? Is that just like a lack of this hormone?
It could be. So a reason for that may be because they're underproducing aldosterone. Other questions? Yes.
I didn't get where was it?
Oh, the adrenal gland. So it says adrenal cortex, but we're going to switch that to the adrenal gland. Other questions? Okay, functions. This is kind of, again, so this is now on that third part. What does it do? What's the effect that aldosterone has? Well, we have a general effect in its nickname, the salt-retaining hormone. But these are now the more specific physiological effects or mechanisms that aldosterone has on the urinary system. So first off, it stimulates the reabsorption of sodium and the release of potassium. And we can think of this in terms of a simple model. So if this represents any tube of a nephron, and we have some cell, well, we can have sodium-potassium pumps that just do what sodium-potassium pumps do. If there is sodium out here that we need, well, then a sodium-potassium pump is going to move sodium in one direction and move potassium into the tube. So we retain sodium by releasing potassium. So all that's necessary is just to run sodium-potassium pumps on the surface of these cells. Now, typically, we've talked about sodium-potassium pumps running in the opposite direction, right? Sodium out of the cell and potassium in, but nothing says that we can't turn the sodium-potassium pump around. So by pumping sodium in and potassium out, we don't have to worry about that cell maintaining a resting membrane potential to carry out an action potential. It's not a neuron, it's not a muscle cell. So we can reverse that sodium-potassium pump, and we can accomplish at least two of the things that might trigger its release, right? So if we run that sodium-potassium pump, we are getting rid of potassium while reclaiming sodium. As we get the sodium, and this sodium is going to the bloodstream, right? That's that's where that sodium is headed, eventually to the bloodstream. Chloride ions that are also present in our urinary waste are attracted to the sodium. So they're pulled along with the sodium just through electrical attraction, and so that's how we get to reclaiming sodium chloride. So that's why it's referred to as the salt retaining hormone, because we're pulling lots of sodium out, chloride follows by electrical attraction, and so in reality we're reclaiming sodium chloride. We also know that through osmosis, water is attracted to that particular solute, sodium chloride. So we get sodium, we get chloride, and then we also get water. Water is attracted to where the sodium and the chloride go. Water going to our bloodstream is going to increase the blood volume and therefore increase the pressure. So where the sodium chloride goes, water follows. Where water goes, volume goes up, and therefore the blood pressure can come up inside that blood vessel. The other net effect is that if we are sending more water back to the bloodstream and more sodium, the result is I'm going to have a reduced urine load because water is going back to the bloodstream. I'll have a reduced urine load, but it will also be high in potassium concentration. So if we wanted to know indirectly whether or not aldosterone is having a significant effect on urinary production right now in the body, rather than sample the bloodstream and test for the presence of aldosterone, if we just know that we have low urinary output with high potassium levels in that urine, pretty good indication that aldosterone is having its effect on the urinary system. So again, we might engage in aldosterone production because we want more sodium, but getting that sodium also means getting more chloride and therefore getting more water, which is going to help us bring our blood pressure up. So we might secrete this hormone for various reasons, but that's the net effect. We get sodium chloride and more water and less potassium. Questions on aldosterone and the effects that it will have on the urinary system? Okay, so that's our first one. We'll go on to number 2, nature-edited peptide hormone. This one comes from the heart. It's actually produced by the myocardium. The muscle of the heart itself produces this particular hormone. So that's our, again, our kind of low-hanging fruit, the easy one. Simply know, and if you just tell me the heart, that's fine. You don't have to be as specific as saying the myocardial layer of the heart. It comes from heart. It comes from heart. It comes from the heart. It has 4 actions, okay? But we're gonna hit our second bullet first, which isn't properly stated in this PowerPoint slide. So we're gonna narrow it down to just one major thing. So it has 4 functions, and it says thus reducing blood volume and blood pressure. So let's tie this to when is it released? It is released when our blood pressure is too high. It might be released for other reasons, but that is going to be the primary reason by which this hormone is released into the bloodstream. When we have too high a blood pressure for too long, this hormone will be released. So for this one, just know that singular most important cause for its release. So for this one, we can now think of its actions in almost perfect direct opposition to what we just saw here. If we hold on to sodium and chloride and water, blood pressure will go up. But right now, we're releasing this hormone because our blood pressure is already too high, so we want all of those things not to happen. So the net function here is to increase the amount of sodium and chloride that stays here. So we're not doing that. We're increasing the sodium chloride level in urine And now that is going to do the opposite. It will actually pull water back into the urinary waste tube, reducing our blood volume. And when we reduce the water volume in our blood, essentially our plasma level, then blood pressure will come down. So that's the general effect, but we're going to get into a few specifics here on how we accomplish that. So, one specific function. If you have high blood pressure, one of the ways to reduce high blood pressure is by producing more urine. The more fluid you can get out of your body, the lower your blood pressure will go. So this is one mechanism by which we can lower blood pressure. We have to be careful here because, of course, there's the point at which we can become dehydrated. We can have electrolyte levels that are beginning to swing in directions that we don't want them to. But generally speaking, if our blood pressure is high, we urinate more, less blood volume, less blood pressure. So how do we get to urinating more? I need my GFR to go up. I need my glomerular filtration rate to increase. The higher that goes, the more urine that I produce. So how do I get there to a higher GFR? Well, we've talked about a variety of ways, but the specific effect that this hormone has is to do this. It dilates the afferent arteriole and squeezes down on the efferent. What is that going to do to the pressure inside that blood vessel? It's going to cause it to skyrocket. So that pressure is going to go up, therefore I am filtering way more fluid than I ordinarily would. So that causes my GFR to climb. More water going into the waste tube, and I produce more urine, therefore less blood volume, therefore lower pressure. So that's the primary function of natriuretic peptide hormone. Increase GFR by dilating the afferent, more fluid in, squeezing the efferent, less fluid out here, therefore more urine production. The other function is pretty straightforward. It inhibits the production of those three molecules, renin, aldosterone, and antidiuretic hormone. Each one of those work to increase blood pressure. So this hormone kind of cancels out these other three that would otherwise on their own work to bring blood pressure up. So right now we have high blood pressure, so we don't want to secrete these three hormones that actually work to increase blood pressure. So this hormone counteracts, in fact, inhibits the other three. And then lastly, it says inhibits sodium chloride reabsorption by collecting duct. That simply means that sodium stays in the tube instead of being reabsorbed to the body. Wherever sodium stays is where water goes. Water is attracted to the sodium chloride, it's attracted to the salt. So that last statement is basically saying we're leaving the sodium in our waste tube, and therefore water will stay attracted to it and will increase the amount of water that leaves the body, thereby helping to reduce systemic blood pressure. Okay, so I've got one now that works to help increase blood pressure, and one now that works and helps to reduce blood pressure. Questions on those two? All right, next up, antidiuretic hormone, ADH. So this one, antidiuretic, anything that's antidiuretic means that we are going to produce less urine. We're going to conserve water. Where does it come from? As long as you know the pituitary gland, that's fine. It says the posterior of the pituitary gland comes from the pituitary gland. So this is the base of the brain. When is it secreted? When we are dehydrated. That's going to be the primary reason for its secretion. Whenever we are dehydrated and we need to conserve water, this hormone will be released. Its net effects are pretty straightforward. Antidiuretic hormone makes the collecting duct more permeable. So tying this into what we described last week, remember the collecting duct is taking water out of the kidney. We said that the nephron loop created this salty environment out here. That was the function of the nephron loop. So as water passes down the collecting duct, it is attracted to the sodium. And so if I want more water to come out of this collecting duct, because if it stays in, it's going to the bladder. If it goes to the bladder, it's lost to us. So if I want more water to come out of the collecting duct before it ends up going to the bladder, I make this tube more permeable. You might remember the name. I put more aquaporins. Those are the little channels in cells. I basically install more aquaporins, making this more permeable. More water is drawn out to that salty environment that surrounds the nephron loop. And therefore I conserve water. Any water that is pulled out and is attracted to the NaCl, it tells us down here at the very bottom, that just means that water is going to the bloodstream. So even though it isn't directly mentioned in this slide, and it is a consequence of this action, what's going to happen to blood pressure? What's going to happen to blood pressure when we secrete antidiuretic hormone? Blood pressure going to go up or down? It's going to go up. So even though it isn't necessarily secreted because of low blood pressure, this will also help combat low blood pressure. Question, that was a little more straightforward. Questions on that? All right, one left. Last one, parathyroid hormones. Low-hanging fruit for this one. Where does it come from? The name tells it all. It comes from the parathyroid hormone. All right, comes from the parathyroid. Comes from the parathyroid hormone. It tells you up at the top the primary reason for its secretion. When we are hypocalcemic. So this one is secreted for a very specific reason. When we don't have enough calcium in the bloodstream. So when we are hypocalcemic, this can cause disruptions in resting membrane potential, which then, of course, leads to an inability to contract muscle and carry out normal nervous system physiology. Our action potentials are thrown off when we don't have the right amount of calcium in our tissues. So hypocalcemia can be quite dangerous quite quickly, so we have to work to restore calcium levels, and this is one way. There are other ways as well. Calcitriol can have an effect, calcitonin can have an effect, but parathyroid hormone is a pretty potent hormone when it comes to reestablishing calcium levels. So again, straightforward, where does it come from? Parathyroid gland. Why do we secrete it? We secrete it when we don't have enough calcium. So how do we get to having more calcium? It says that it acts on the proximal convoluted tubule to increase phosphate excretion. We'll explain why we do that in just a moment. So we haven't mentioned phosphate at all in the urinary system, but all it's saying is that we're putting more phosphate into the waste tube. And we'll explain why that helps us restore calcium levels in just a second. So we're putting more phosphate into the waste tube, meaning urinary phosphate levels go up. We're producing more phosphate in our urine. The second bullet, pretty straightforward. It simply tells the cells along the tubules, whether it's the proximal convoluted tubule, distal convoluted tubule, it says, hey, if you see any calcium out here, absorb it. We want it back into the bloodstream. So it encourages the cells of the tubules to just increase the rate at which they're reabsorbing calcium. They already have a default state of reabsorption. We just increase that. We kind of talked about how we might do that last week. Remember with the transport maximum, there's a certain number of transport proteins up here. Well, I can increase that. I can increase the number of proteins that are absorbing calcium, and now I can get more calcium out of what would be my urinary waste. We're gonna do the third one last. Let's do the fourth one. Parathyroid hormone stimulates calcitriol synthesis. Calcitriol goes by a more common name, vitamin D. Calcitriol is vitamin D. It's the active form of vitamin D. It is vitamin D. So why is it doing that? Because calcitriol, I'm sure we all remember our bone unit, stimulates a cell called an osteoclast. Remember what osteoclasts do to bone? They break down bone. They're bone dissolving cells. And if this represents a bone, what that means is osteoclasts eat away at the bone, releasing calcium to go to the bloodstream. So parathyroid hormone tells the body to secrete more calcitriol. Calcitriol stimulates the osteoclast to get to work eating away at bone, releasing the calcium that is otherwise stored in bone to the bloodstream. All right, and then for this third one, we have to go back and revisit just very briefly the relationship between bone tissue and the bloodstream. Bone is always doing this. It is always taking calcium from the bloodstream and at some level returning calcium back to the bloodstream. So there's always this circulatory path of calcium absorption by bone tissue and calcium release by bone tissue. Now remember, the reason we secreted this hormone is because we said that within the blood, we have low calcium levels. We're hypocalcemic. So right now, I want this to occur, right? And I do not want that to occur. Well, I'm getting here by stimulating those osteoclasts. That's what gets me to releasing more calcium back to the bloodstream. But if I'm continuing to reabsorb it, that's problematic. I'm not getting anywhere, right? I'm just kind of trying to walk to the first floor on the stairs that are coming down. So I'm not going to get anywhere. So I need to stop that. Well, how do I stop calcium from coming out of the bloodstream and sticking into bone? The only way that calcium can actually stay in bone if it connects to phosphate. Calcium and phosphate have to come together in order to calcify and stay in bone. But what was the first thing that we did up here? We sent phosphate to the urinary waste tube. So now there is less phosphate available to stick to calcium. Therefore, that calcium comes in and has to cycle back to the bloodstream. So that tells us why we are secreting the phosphate. We are secreting the phosphate into our urinary waste so that when the calcium comes out of the urinary waste, it can't go stick in our bone. We want it to stay in our bloodstream. So those four things are going to help us hopefully quickly restore our low calcium levels. We have to get rid of phosphate. We have to tell the kidney to absorb all the calcium that it can. We have to get those osteoclasts to work. And then by, again, removing that phosphate, calcium ions can't stick to phosphate ions, which is the only way that calcium is actually absorbed by bone tissue. questions on the effect parathyroid hormone will have on calcium levels and how the urinary system plays a role there? All right, there is a myriad of other hormones, lots and lots of other hormones, but we'll say those are our four primary. So again, for each one of those, know where they come from, when do we secrete them, and what are they going to do? What's their mechanism of action? Good on those?
On the last one, on parathyroid, does it increase blood pressure by doing?
It does not have, I would have to double check myself. I don't think it has any significant impact on blood pressure, parathyroid hormone. Other questions? All right. So moving past our hormones, let's see. This one is pretty straightforward. Basically, it says again that once we have modified the urine chemically, we've decided how much sodium, chloride, calcium, phosphate, potassium, whatever it is. Once we have modified the chemical composition of this tube, once that waste goes into the collecting duct, and I've said this before, but once that waste goes into the collecting duct, the only thing that we're doing at that point is deciding how much water to pull out and how much water to leave in. So in stage 3, in water conservation, we're just going to leave it that simple, that in stage 3 water conservation, we have chemically modified our urine. We've decided exactly which electrolytes we're keeping, which solutes are staying. In stage 3 water conservation, all right, sorry, that should be stage 4, I apologize, I misnumbered that. So just to recap our stages, stage 1 was filtration, and the numbers don't matter, but we need to know the 4 events. So one event was filtration, which we can think of as stage 1. So stage 2 was tubular absorption, stage 3 was tubular secretion, and now this is water conservation. So we've talked about each one of those events, but water conservation, again, just deciding within that collecting duct, how much water are we going to pull out? Again, I think this slide is just mentioning nothing new that we've already talked about. Nephron loop, creating the salty environment, water passing through the collecting duct, attracted to the sodium chloride. We can modify how much water leaves through manipulation of the permeability, and we just saw that with the hormones that we just saw. So collecting duct, through its permeability, is going to affect how much water ends up in our urine versus how much goes back to the body. I'm going to jump past the picture, and getting to the end of our PowerPoint now. Most of the back end of this PowerPoint is now just vocabulary, some terms that you need to be familiar with, and some values, some specific values for the urine. We'll start off with specific gravity. So these are kind of urinalysis. The specific gravity of urine is slightly higher than water. Water is 1 gram to 1 milliliter, perfectly. Pure water is just 1 to 1. A milliliter of water will weigh a gram. Urine is going to be just higher than that because it's going to be water, but then it's going to have solutes in it. So the specific gravity of urine is just barely over 1 gram per mil. So just slightly higher than water. The osmolarity, blood is around 300. You can see that the osmolarity of urine ranges greatly from below normal blood osmolarity, so down to 50, but up to 1200. So all of those are within the normal range. So the higher it goes, this would indicate the more dehydrated a person is. The lower the value, down to 50, that would indicate state of high hydration. Another way of thinking about it, the lower the number, the more urine you're producing, the more water that is present in your urine. The higher this number, the more concentrated your urine, the less urine that you're producing. So that's the osmolarity. So it's basically a comparison of how much of your urine is water and how much of it is solute, like sodium and, well, the things that we just mentioned might be in it. So when the number is higher, it means there are more waste and electrolytes in it. And when the number is lower, it's getting closer and closer to just pure water. pH range, again, quite a bit of variance here, somewhere between 4 and 8, and then on average around 6. That's the normal pH. So typically slightly acidic. And then chemical composition, as any fluid in our body, this would be true for any fluid in our body, it's mostly water, so 95% water, and only about 5% solute. And then at the bottom, these are not normal solutes, these are the abnormal solutes. So that it would be unusual to find any significant amount of glucose, hemoglobin molecules, albumin. Remember, we said at the very beginning when we were talking about filtration, proteins should not be filtered out of the bloodstream. Hemoglobin's a protein, albumin's a protein. So if we're seeing proteins in urine, means maybe that filtration membrane's breaking down. Something's wrong if we're finding protein in the bloodstream. Ketones, if we find ketones in there, it means we might have some metabolic issues like diabetes. And then bile pigments. If we're producing too many bile pigments, maybe we might have liver issues or something going on with our spleen, but in any case, those are the abnormal solutes that we would not want to see in urine. Questions on any of those values? All right, again, just more definitions. We've already talked about the very top one. We need to know that normal urine output is somewhere between 1 to 2 liters per day on average. The term for excessive or greater than 2 is polyuria. So that is producing on average, maintaining greater than 2 liters per day. Oliguria, this is less than 500 mils per day. And then anuria is between 0 and 100 mils per day. So essentially we're not producing, I mean, obviously 100 mils is an amount, but we're essentially producing next to nothing when it comes to urine output. Any number of things can lead to anuria. Down here, though, is a specific value that I want you to pay attention to. When we get below 400, that cannot be maintained for more than just a few days. Right? We can't continue to maintain low urine production at that level because the nitrogenous waste levels in the blood will increase too much. And that's problematic for a variety of reasons. Only somewhat tied to polyuria, a diuretic is just any chemical that increases urine production. So again, we're just going through some vocab. Questions on those? All right, urinary tract infections, terms that relate to urinary tracts and infections. Cystitis. This is an infection. Typically, we describe it as an infection of the urinary bladder, although you could include the urethra there as well. So basically, from external urethral orifice to the bladder, if the infection's there, cystitis. If the infection is above the bladder, say up the ureter, up to the renal pelvis, pyelitis. If the infection is in the urinary system and has actually gotten into the functional tissue of the kidney, so it's in the cortex, it's affecting the nephrons, then it's pyelonephritis. So a urinary tract infection is actually now impacting the functionality of the nephrons that we've been talking about. Often those infections are caused by bloodborne bacteria, while the other two, cystitis, pyelitis, those might be environmental agents that lead to those infections. But the third one, typically a bloodborne bacterial infection, is the only way to get to the most damaging, problematic urinary tract infections. Questions on the vocab there? Okay, let's see here. I'm gonna things there. We don't have have cause to go into each one of those specifically. So we don't worry about the cause of nephron destruction, but what renal insufficiency is, most often, is caused by nephron destruction. So we lose nephrons. Remember, we have millions of them in our two kidneys combined. And even though we're not going to go into the causes specifically, we will at least mention one that we've already talked about, hypertension. We said previously that filtration pressure inside the glomerular capillary is 60, and ordinarily in a capillary, it's 10. So it's 6 times higher than elsewhere in the body. That puts that particular capillary at great risk of essentially the prolonged consequences of hypertension. So hypertension, even we're not going to say it's the most likely cause, but it is at least one cause that we've talked about previously, that hypertension can lead to nephron destruction, and the more and more nephrons that become dysfunctional, the less efficient our kidneys will be. If, for example, we are experiencing pyelonephritis, the kidney can regenerate. So the nephrons can bounce back. So if it's a short-term, temporary effect on nephron function, then the kidneys can bounce back. But comparatively to, say, the liver, the kidneys don't have great regenerative capabilities. So hypertension being long-lasting, typically there isn't recovery, nephron recovery, from something like chronic hypertension, the effect of which accumulates over time. But if it's just a bacteria infection causing damage to nephrons, and in short term, we're talking maybe like weeks, the nephrons are going to bounce back from that. Down at the very bottom, if we lose nephrons, or if a particular subset of our nephrons are experiencing a bacterial infection, the other functional and healthy nephrons will kind of take over for the dysfunctional and perhaps diseased nephrons. They go through what we call nephron hypertrophy, which simply means they get bigger. So we might have fewer functional nephrons, but the nephrons that we have that are functional increase in size. And as they increase in size, then their filtration capabilities goes up. Now they can only do that to a point though, to compensate for nephron loss. But it is something that happens. We get nephron compensation for dysfunctional nephrons through what we call hypertrophy, which again just means increasing in size. Questions there? Let's see. A couple of interesting key points. Even though we have 2 kidneys, a third of one kidney can maintain our filtration needs in and of itself. So we can get by with quite a little amount of our total functional nephrons and still maintain good good filtration capability. So 1/3 of a single kidney is technically capable of filtering the metabolic waste that we produce in a particular day. So when 75% of nephrons are lost in total, we do though drop significantly in our total urine output. And when we get below 30 mils per hour, this is what we call renal insufficiency. This is now, when we get below 30 mils per hour, this is an inadequate amount of filtration to get rid of nitrogenous metabolic waste. That's when we have azotemia. And we started maybe on slide 4 or 5 by defining azotemia. Azotemia is an elevated blood nitrogen level, and we're experiencing some level of kidney failure at that point. Acidosis sets in, the acidity level of our blood increases, we become anemic, uremia develops, which means, again, low urine production. And at that point, we got to go on hemodialysis. So the kidneys aren't filtering the blood efficiently. We have to get into a state where machines are doing it for us. Don't worry about we're not gonna worry about exactly how it does it, because that last bullet doesn't even come close to adequately describing how those machines work, but just know that hemodialysis, which I suspect you already do, is a machine doing the job of the kidney. Questions there? All right, try not to get too conceptual at the very end there, just really wanted the last bit to just be some terms to be familiar with. Conceptually, we'll kind of wrap things up with the hormone levels. All right, that's it. That is our last day of actual lecture material.